Using a row of shrubs as one side and fencing for the other 3 sides, a rectangular playground will be constructed. Given that there are 120 yards of fencing available, determine the dimensions that would create the area of the playground of maximum area and identify the maximum area. What am I trying to do? I'll put that in green. Maximize area. I'm maximizing area. That's omega. My objective. My objective is to maximize area. Okay, I need to maximize area, and I'm going to do so subject to a constraint, and the constraint is that there are 120 yards of fencing available. That's my constraint. We should draw a picture. Some shrubs. Those exist for free. And then we're going to do some fencing, and that's my fencing. And we're going to put a playground in here. Look, it's a playground. I'm going to draw a swing set. Look, it's a playground. Oh, we're going to maximize the area of that. I know that since it's rectangular, those 2 sides have to be the same, and then the other one is allowed to be different. We should probably come up with names for our variables so that I can actually work with coming up with a formula for the area, because until I have a formula, like, this isn't going anywhere. So choose labels. We're going to choose that one to be X and Y. We could let them be like A and B, or like W and H. What you call them doesn't matter. I'm using X and Y. I know that omega is X times Y. Product of those things is the area inside that rectangle that I'm hoping to compute. Look at it's too many variables. It's too many. We're going to eliminate one of these variables. We need to eliminate one of X or Y, or we're getting nowhere. This is where the constraint comes in. There are 120 yards of fencing available. That means that the sum of those 3 sides is going to be equal to 120. That means that X plus Y is equal to 120, or 2X plus Y equals 120. And I'm going to use that statement to eliminate one of those 2 variables. I think I'd rather eliminate Y because, like, it's easier to solve for in the constraint at this particular time. It usually shouldn't matter. It doesn't. In fact, doesn't matter which one you choose to eliminate. So we'll go Y equals 120 minus 2 times X. That says that the total length of the fence minus twice that minus those gives you the remainder. That's all that says. And so I'm going to take and eliminate a variable by going Y equals 120 minus 2X, which means that omega is equal to X times 120 minus 2 times X. Now I've got a single variable objective function. Good. And once I have a single variable objective function, the objective function exists to be optimized, and I will do my best to optimize it. I think that it's really good to plot your objective functions. So as a tool for doing better work, I'm going to graph omega. And I can tell that omega is a downward opening parabola, and it has roots at x equals 0 and x equals 60. So I've got a downward opening parabola, and it goes through 0 and 60, and that this is omega equals area. It's a plot of the area. And we know that it's a parabola, which means that the optimum should occur in the middle. So we can predict then, without even computing critical points, that the maximum value should come from omega x equals 30. That means that these side lengths here should be 30 when it's optimal. And I get that from looking at a picture of a graph of my objective function. Let's use that now to help guide our work as we compute the critical points of our objective function. They're going to occur when omega prime equals 0 or omega prime equals undefined. And I know that there are no critical points that are undefined because it's a parabola, and there are no places a parabola has undefined derivative. So I'm going to start by going omega equals 120x minus 2x squared. And then I'll take the derivative, omega prime equals 120 minus 4x. And then I'm going to set that equal to 0. And then I'm going to have that for x equals 120, which means that x equals 30. Oh, it checks out. 30, halfway between, because it was a parabola. If it was a cube, it wouldn't be halfway between. Wow, that was awesome. So we found that x equals 30. Okay, so we found that that length there is 30. And I know that because y equals 120 minus 2x, then y equals 60. So those are the dimensions. So 30 by 60 area, and the maximum area is 1,800 square yards. So that's the basic process for solving one of these problems. And I know I didn't write down which step I was doing as I was doing it, because I feel like it's kind of fluid as I go through it. I start by drawing a picture and labeling things. I come up with my objective function. In this case, I needed to eliminate one of the variables that comes from the constraint. And then I get a single variable objective function. Once I have my single variable objective function, I turn a crank. I take the derivative, I set it equal to 0, I solve, I figure out which one of the critical points is the one that I wanted. For a few of the problems, the optimum occurs on the boundary, but not on this one. The boundaries were when the area was 0 and the area was 0, and I'm not interested in negative fence length because I cannot incur debt in terms of fence length. I cannot have negative fence length. What about negative area anyways? This is considered one of the canonical optimization problems that you will see in any Calculus 1 class. Every Calculus 1 class will do a problem like this at some point. What do you think is the hardest part about the problem that we just did? Yeah, the setup. It's all about, just like it was with related rates, right? Yeah, writing the objective function. And that's why I focused on, in this slide, the first 3 steps. Come up with the objective function. That's the hard part. And how do you get good at it? Just do lots of problems. There's no way to get good at this except to do lots of problems.